We're going to talk about ram air wing aerodynamics. So for all ram air wings, parachutes, paragliders, and speed wings, the focus of it will be on parachutes and speed wings. A little bit about me. You guys don't, most of you guys know me, some may not. I've been paragliding and speed flying for about 15 years and skydiving for almost 28 now. Got a few hours flying airplanes, done some engineering. I got a bachelor's and a master's degree. I'm licensed and I still practice in about 10 different states. I'm also lead designer here at Fluid Wings. So I design a lot of parachutes and some paraglider, speed wing stuff. Designed over 20 different models at this point. Done a ton of CFD. CFD is computational fluid dynamics on wings and vehicles. Lots of stuff. So probably most important part is that I still actually fly the stuff. Foot launch, jumping, probably more jumping these days than foot launching stuff, but still active in both. So tonight I kind of want to focus on low speed aerodynamics. So low speeds in an aerodynamics world is defined as nowhere near the speed of sound. So we're going to say in really, really low Mach numbers. That pretty much applies for all general aviation, aircraft, gliders, paragliders, and parachutes. And probably will hold true for a really long time. I don't see us breaking Mach anytime soon. I'll ask you tonight to pay attention and listen and understand that what I'm telling you may not be what you feel sometimes. That's totally normal. It happens in airplanes too. What you feel versus what's actually going on for aerodynamics are very often very different. The aerodynamics is often very counterintuitive. So what people feel and what's actually happening with the airflow across the wing and what's actually going on can be two different things. So we're going to focus on what's actually going on the wing tonight, and we can correlate to that to what it feels like a little bit. But it's important to understand what's going on. And in an aircraft, they talk about this a lot, flying seat of the pants versus instruments. And so seat of the pants is literally when you're flying an airplane or an aircraft and you feel the feedback on the seat. Turns out that actually breaks down sometimes when you have a lack of visual references. And the same thing can happen with airflow. So we're going to fly tonight using instruments and more technical jargon. For aerodynamics, the science is pretty well settled for low speed stuff. There's not a whole lot of new stuff coming. So be wary when you hear the idea or the conversation that I've got this theory in aerodynamics. We've really kind of solved a lot of this stuff. We haven't done a whole lot new in low speed stuff. Now, what we do is we find new ways to capitalize on these existing understood mechanics and how it works. And the future advances are all going to live there in new ways of solving the same problems. But understanding how it works and what's really going on is kind of settled science. Most of what we're going to talk about tonight is going to be steady state, not dynamics. And so we'll define steady state as, we're not going to be accelerating. So it's zero acceleration for a lot of the stuff we're talking about. We're going to talk about a lot of vocabulary. We're going to talk about how the airflow flows around a wing, and we really delve into defining all the parameters for that. We're going to talk a little bit about how the airflow affects the wings and flying through different columns of air. A little bit about glide ratios, angles of attack, stability, and then basically start talking about, we'll kind of wrap up with some basic turn mechanics. That'll be it. And it should take us about an hour plus tonight, plus some questions. So I'm going to jump right into it, and we're going to get going on some basic terminology. So everyone, you may know this stuff, you may not, but this is how we're going to refer to things for the rest of tonight. And if you use these as you're talking about things in the future, you'll find that your conversations about flying become a lot more clear. So pitch is the movement around the axis. This controls whether we're going nose down or nose up. Roll is side to side. And yaw is swiveled side to side, changes the direction you're looking. On a parachute, these are all coupled together. So you can't really get one without the other. They don't have a rudder. So if we had a rudder, we could get yaw just individually, or we could get roll individually, or we could get, with an elevator, you can get pitch individually. But because we're a deformable wing under a pendulum weight, with a pendulum weight under it, sorry, they're all coupled together. And there's a few ways we can get these, but these are the basic axes we're going to talk about of movement. Another thing we're going to talk a lot about, and you'll hear me mention a lot, this and future seminars, but trim speed. So when you set your wing up, it's set to fly at a certain angle of attack and a certain glide ratio when you go hands up. And don't give any inputs. So it's kind of the natural flying attitude of the wing with your wing loading and your geometry and your body. And that's going to be the trim speed. So if you're on a speed wing or a paraglider, you could be putting speed bar in or brakes. Speed bar would be to speed it up and decrease the angle of attack. Or you could be using brakes to change your glide ratio as well. But in this conversation tonight, trim speed is going to be really just that steady state, no input flying. So most higher aspect ratio wings like paragliders, they achieve their best lift to drag pretty close to their trim speed. So you flatter the wing, higher aspect ratio, generally they're going to be getting their best lift to drag, their best glide ratio, right at where they're trimmed or pretty close. For parachutes and speed wings, the two deviate quite a bit. So our trim speed is going to be nowhere near the best glide or the best lift to drag on a parachute or speed wing. So that can be a useful topic and a useful way to understand your wings is when you're talking about is a wing fast, slow, or how's it trimmed. Talking about the trim speed can tell you a lot about a wing. So I'd like to introduce that technology. That terminology. It's pretty widespread in the paragliding world. I don't hear it as much in skydiving, but I'm starting to hear it more. Descent rate, pretty simple. This is just the vertical speed. So you're going down at a certain rate and you're going forward at a certain rate. In the US, we usually use feet per minute. In most other countries, they would be meters per second. So descent, let me go back. Descent rate is just it's a common thing. A lot of people get total speed and descent rate mixed up. They can perceive descent rate a lot better than they can total airspeed or trim speed, and they'll mix the two up. So I wanted to take a moment here and kind of delineate these for people so that they understand what you get on your fly site is probably just descent rate. You're probably not getting a good trim speed because you don't have a venturi or a pitot tube. So now some hang gliders are jumping with pitot-static systems, but I don't know any skydivers. So let's talk a little bit about the airflow across a wing. This is kind of the drawing you're going to see a lot of tonight. I just want to run through it really in detail here and take a few seconds. You look right at the front of the wing, and right out here, that's the leading edge. So a lot of people call it the nose, the beak, whatever you want to call it. It is the leading edge. That's the proper term. And then at the trailing edge, it's not the butt, it's not the tail, it's the trailing edge. If you draw a line between these two spots, you get the chord line. Chord line is something that you'll hear aerodynamicists talk a lot about. People who are building airplanes talk a lot about the chord line. It is from the leading edge, the furthest forward point to the forward, and the furthest rear point. Straight line between the two is the chord line. See, that's a straight line. The dashed line above it is called the camber line. And the camber line describes the curvature of the wing. So the chord line and the camber line are not always the same thing. They're usually not the same thing. So it's important to realize the difference between the two. And the angle between the chord line, which is a straight line, and the airflow on the wing is called alpha, or the angle of attack. This is a really key point here, guys. And it is then I'm going to beat it into you tonight, and there's a few reasons for it. It's probably the most useful concept in all of aerodynamics. Understanding angle of attack and understanding what happens with angle of attack is probably the single most useful concept, and it's probably the most misunderstood among users. I hear angle attack referred to as all kinds of different things. Typically, people are associating their angle of attack with their glide ratio, and there's a big confusion there. So angle attack doesn't care anything about what it's flying over the ground or distance it's covering. It only knows the distance between the angular dimension between the chord line and the airflow. So it's that little squiggly sign, that's the Greek letter alpha. That's what aerodynamicists like to call it. You'll see alpha, AOA, angle of attack. Think about the relative wind as a skydiver, or as if you stick your hand out the window when you're driving down the road, you can vary the angle of attack on your hand by changing the angle you hold it at. So when we rig up a wing, you've got the rigging angle and the angle of attack. And they're both contained between horizontal and the glide path, if you look at the top here. So again, this is the angle at which the airfoil's chord line meets the relative airflow, alpha. So let's talk a little bit about best glide. So best glide, or best L over D, or glide ratio. The best glide would be the glide ratio where the wing flies the furthest relative to the air, not relative to the ground. Now, in completely still air, that'll be the same as the ground, but in moving air mass, the two aren't going to correlate. So all your wing cares about is the air when it's flying. It does not care about the ground. It doesn't see the ground. Only you do. So one of the things you can look at is our handy little graph over here. And this talks about how to find your best lift over drag. And I think this is one of the profiles we used in the HK3. I'm not sure. But if you look at it on the left, the vertical axis, that's your coefficient of lift over coefficient of drag. And then on the horizontal axis, you see the angle of attack. That's 0 degrees, 10 degrees, 20 degrees, and 30 degrees. What's important to realize from this is the angle of attack that the wing is flying at determines the glide ratio in large part. And so there's an optimal spot there. You see the top of the curve where it gets the best coefficient of lift over coefficient of drag, which I'm going to do a spoiler here, is your glide ratio. I'll tell you that in a couple slides here. That gives you your most efficient gliding response for the wing, and it varies over angle of attack. So it's an important concept. See, that's just one of the many things that angle of attack is going to affect on how your wing operates. So let's talk a little bit about how the equations and how the math works a little bit on this. So in flight, you've really only got 3 forces acting on you. And we're going to kind of gather up all the lift and put it in one arrow. And we weight that arrow by how much pressure is in different spots, and you integrate all that, and you get a resulting lift vector, and it acts at a certain spot. You can do the same thing with drag, and so some of the drag acts on the parachute, some acts on the lines, some acts on the pilot. So the drag acts a little bit further down. And we're going to resolve that into one force called drag. And then there's weight. So those are the three basic things that are acting on you in flight. If we had a motor, we'd have to put thrust in there. So how do we determine the lift? Let's look at what the lift actually is. So for aerodynamics, we've simplified the lift and drag equations to be coefficient of lift times 1/2 rho v squared times s. Rho is that little p. It's the Greek letter rho. It's actually air density. V is the velocity, and s is the area of the wing. So aerodynamicists like to use s for the wing area, so it doesn't get confused with other areas that are used for, say, drag calculations. We'll see down here that the drag force is 1/2 rho v squared, coefficient of drag, times a, and a is just the area that drag acts on. Now, drag is going to act on the lifting surfaces and the pilot and the lines, so you get a bigger a than you do s areas. The important thing to realize on all of this is everything's a linear relationship except for one value here, and that's velocity. Drag goes up as a square of velocity, and so does lift. So it's just an important detail to realize that everything else is linear except for velocity. It is an exponent, so it matters way more in all of the calculations we do. So we got three forces, like we said. A lot of people struggle with this a little bit too. So in static flight, as long as static flight means a steady state, there's no acceleration, no changes in velocity. So that means you're not accelerating either direction. Well, if you're not accelerating either direction, your lift must equal your weight. Let that sink in for a second. Lift is weight in static flight. Okay. So now let's take these same equations and let's look at our lift to drag. Just so happens that glide ratio is lift over drag, guys. So remember, we said we're only dealing with a couple forces, right? We've got three forces. I resolve them. My glide ratio, the distance I'm going to cover over the ground, is my lift divided by my drag. Well, because we have common factors there of 0.5 or 1/2 rho v squared times a, you can cancel both those out. And you get your lift over drag is your coefficient of lift over the coefficient of drag. So in static flight, if you know your glide ratio, you know how much you weigh, you know your drag. So it's kind of neat. For example, someone who's flying at a glide ratio of 2.0 and is 200 pounds, we know that their drag is 100 pounds. So kind of cool. It's a really handy direct relationship. So it's something you can experience that is actually the aerodynamics when you're out flying. And I love it because it's one of the few things that's not always apparent to people right up front either. And so this is a really powerful tool when you learn it and understand it. So let's talk about what happens when things change in the air mass, right? So you've got a thermal. So we're not always flying through calm, steady state air. So let's look at a thermal. What does a thermal look like? So this diagram of a thermal is out of the FAA glider handbook. It is really accurate. So in the center of a thermal, you have lifting air. It hits a certain point where it stops, slows down, crowns off the top, and at the difference between the two, there's really spinning rotors and then descending air on the outside of it. Then on each side of it down at ground level, you're going to see suction causing horizontal flow. And that horizontal flow goes in, fills in the cavitation from the lifting air. The important thing for us to realize is that whenever we see lift, there's usually some sort of sink nearby. They kind of come in a pair, right? Well, that's not the only kind of turbulence we get. We get mechanical turbulence too. So if you've got lift, say on a mountain, or this could be a building, it could be a lot of things, but you're going to get, as it forces that orthographic change in topography, it creates an orthographic lift here. And so you'll get air flowing upwards over the mountains, and behind each of these peaks, you get a rotor. That rotor can be a series of descending or lifting air, but usually it's very, very turbulent there. Now on the lee side, depending on how the top of this is formed and the shape of it and the speed of the wind and the pressure and a lot of different stuff, you could have rotor or descending air. The important thing here is to remember, again, wherever there's lift, there's sink. And when it's mechanical lift, it's usually going to be a lot of turbulence, like rotor. Rotor is bad, okay? A lot of reasons. So let's talk about, so what does lift do to how the wing is hitting your airfoil? So we got sinking air. It's going to decrease our angle of attack. Now the effect is only for a short period of time, and your wing's going to change pitch to reach equilibrium. But instantaneously, when you're going from steady state air into sinking air, you have to add up these vectors. So you've got your normal airflow, and that's flowing at the angle of attack, that alpha that we've trimmed our wing at, and it was flying along in steady state, right? Well, you add in that red sinking air on top, and you resolve those two vectors into a new one, and you can see that it decreases the angle of that angle of attack. So you'll have a decreased angle of attack when you enter sink. Usually when you enter sink, you're also going to feel a pitch change. You're going to feel the wing surge forward to increase its glide speed, because now it's got to accelerate a little bit to make lift equal the weight. Conversely, when you enter lift, it increases the angle of attack. Again, the effect is only for a short time. The wing will have to change its pitch and reach a new equilibrium. But when you've got the airflow there, your airflow is in blue, and the lifting vector is now going up, the red's going up. They both resolve into an increased angle of attack. And you can see that it's a higher angle compared to the chord line of that wing. Well, why is that important? Well, we're going to cover that in a little bit, but it is important to realize that when you change air masses, when you change air densities, when you change airflow, whether it's going up or down, you're going to change the angle of attack on your wing. So let's talk about what happens on angle of attack versus the wing and it's the airflow. Here's a typical coefficient of lift versus alpha graph. So if you look on the left is the coefficient of lift. And again, we know that coefficient of lift really defines a lot of the lift if I know my velocity in my areas. So typically when we're designing, we're using just a coefficient. And we're changing the properties that change the coefficient typically. And the important thing to see here is at the bottom here, really low angles of attack, you get a low coefficient of lift. It continues to climb until you get really high, right? And then what happens there? Well, we get what's called a stall. So an aerodynamic stall is when the wing decreases lift suddenly. It's not losing lift. The lift didn't completely go away. It just decreases. So if lift decreases, then you have an imbalance of forces, and the wing has to accelerate one direction to recover from that. But it is neat to see that out there at the very edge, it's still, that wing is still producing lift. And I'll throw in there, like you think of an F-22, they've got the vectored thrust, and you can see it when they're flying sometimes. They can fly at crazy high angles of attack. And that happens is if you have enough thrust and you can push it in the right direction and keep everything stable, there is lift out on the edges of these curves. It's just not as useful, right? So high angle of attack, you start getting stalls. Well, let's talk about what happens at a stall. And it's important to realize that that stall it's set at an angle. It's at a critical angle of attack. And it's not related to an airspeed. It's generally an angle of attack, okay? So in skydiving or in speed flying or paragliding, we think of stalls a little bit differently. And because at some point we do drastically lose lift. So there's two types of stalls that we typically are experiencing. One is an angle of attack, and that's usually when you're using risers. You're changing the angle directly, and you hit that critical angle and you start to see a sudden decrease in lift. It doesn't completely go away, but it starts dropping pretty quick. When you go to controls, you're doing a different thing. So when you go to controls, you are increasing the angle of attack, but at the same time, you're changing the pressurization and drastically changing the shape. A lot of times the wings lose their shape and their pressurization. So it's a combination of angle and shaping. So there's kind of two different stalls for us. The important thing to think about it, though, is that it's just a sudden loss in lift. It's when lift starts to go away. And usually it's related to an angle. So speed is not going to give you extra margin on this. And the way to think about this for what this relates to us using it every day is you're flying on rears and trying to dig out of a turn or something. Once you hit your critical angle, doesn't matter how fast you're going, you're not going to get any more out of it. Okay. So at low angles of attack, let's talk about that too, because that's an equally important envelope on the flight parameters we're going to get. So we operate kind of weird aircraft. A lot of other wings, if you've got a fixed wing aircraft or a glider, say a sailplane glider, they can experience negative lift and they still maintain their shape. They still keep flying. In fact, some gliders will go, sailplanes will go on their best L over D in still air. Sometimes, or when they're on speed, they're trying to get their best penetration. Sorry, not their best L over D, best penetration to get to the next thermal. They'll actually be at negative lift out on their wingtips, and you can actually see the wings curve downwards because they're producing negative lift at the wingtips, and then most of the lift is coming closer to the root. That is something we can't do on our wings because we have lines, and lines only take tension. They do not do very well transmitting compression. So once you get negative lift on a line, it just folds up and the wing comes down. That typically happens down in that little red box. So the important thing to realize there is that it's not all airfoils is that a negative angle of attack that is negative lift. And some airfoils can have negative lift at a positive angle of attack or negative angle of attack with positive lift still. For example, this one, if you look at the blue line, it maintains positive coefficient of lift clear out to a negative 2 degrees, 3 degrees AOA. So the things that we're scared of, paragliders, speed wingers, parachutists, we're all scared of the collapses and the stuff that comes from an angle of attack or lack of lift out there, negative lift. So this kind of leads us into talking about stability. So I'm going to tell you about stability. This is what aerodynamics people refer to as stability. And then what we refer to as stability as ram air pilots, speed wings, paragliders, and parachutes, they're entirely different. But it's important to understand what an aerodynamicist thinks of stability, because it tells you a little bit about how when you talk about the wings. So the static stability is really the tendency of a wing when you give an input to return to its original attitude, right? So like, if you were to take a wing and turn it and it recovered quickly back to level flight and righted itself, it's got a positive static stability. If it doesn't change and go back to level flight or go back to the original flight attitude and just continues along that path, that has neutral stability, and it really aren't any that we would fly, but if it has negative stability, it's going to move further away from the original attitude and diverge and become wildly unfun to fly, probably, for a parachute or a speed wing. But that's static stability. That's what an aerodynamicist is usually talking about. For dynamic stability, they're talking about the number of cycles it takes for it to come back to the steady state, or to come back to where it was previously pre-disturbance. Something that you don't want to see is a divergent tendency in those, where the oscillations get bigger. That's negative dynamic stability. And if the oscillations become lower, is really what you do want to see, and that's damping. It's said to have positive dynamic stability. You notice none of this has the word collapse in it at all. So when we talk about stability internally, we have to realize that people outside of our microcultures here, they don't understand what you mean. And to an aerodynamicist, it means something completely different. We're going to kind of define some ideas here and maybe use some slightly different terms. But parachute stability is often confused with collapse or deflation and recovery. In paragliding world, they usually call them collapses or deflations. They typically don't call it unstable. But skydiving wings and paragliders kind of have different levels of passive stability. Now, passive stability is going to be, we're going to define that tonight as kind of the inherent ability of the wing to resist these pitch changes or these pitch divergences or collapses without requiring a control input from the pilot. So something with high passive stability would be something that you hit some turbulence, you hit some funky air, and you don't have to do anything. The wing will right itself, and it's probably not going to take a big collapse or any at all. And something with low passive stability is going to be something the second you hit that sinking air, if you don't give a brake or a riser input, you're going to get something, and it's going to give you some positive or maybe less than positive feedback, something that maybe you don't want. So passive stability is the ability of the pilot to not do anything. So in skydiving, passive stability is very high, much less so in speed wings, and in paragliding it's even less so. And that is where we're going to tie back in. A lot of that is tied to angle of attack, right? So we don't use it the same, but almost all of the stuff we say is instability is tied to angle of attack and pitch movement and inflation of the wing. They're all kind of tied together a little bit. But if you get one thing out of this, understand that angle of attack here is the key principle to understanding all of this. So let's talk a little bit about pressurization and how ram air wings are pressurized. Because I hear people talk a lot about pressurization, and it is somewhat misunderstood in a lot of ways. So we basically use stagnation pressure, or ram air, and that's the force or the pressure of the air that's moving or that you're moving relative to as it stagnates against a surface. So for us, it's the pressure when the fluid comes to rest. So you can either imagine the wing moving through the air, and it takes that air and goes from at rest to moving it to the same speed as the wing. Or if you just accelerate the air at the wing and the wing is stationary, when it hits right here, you get that little spot where the air stops, and that's stagnation pressure, right? And that's the only tool we really have to control our pressurization on the wings. So if you look at it, this is the diagram of a wing. This is the pressure distribution. So if you look, you've got negative pressure acting away from the surface up at the front right there. It's a lot of lift. That's good. It resolves down into that big arrow, which is the lift vector. Then as you go towards the front in that straight section, that is right here, and that's your leading edge, and that's your stagnation pressure. So think about stagnation pressure as you're driving down the road and you stick your hand out the window and you're holding it flat. The pressure right there on the hand, that is your stagnation pressure, right? Basically, when we're designing internal pressurization on a wing, or you're trying to keep the wing flying and keeping its shape, you've only got stagnation pressure to work with. You're not going to get any more. Hopefully you don't get less, but hopefully you understand that. So that's a key pressure there to understand, is that you can never get internal pressure on a wing more than the stagnation pressure. High speed, high pressure; low speed, low pressure. Let's look at pressurization on a wing. So you see the graphic there of the wing over here, and you can see this is one that I was flying. I'm going to show you the video of that right next. The one thing I want you to see here is as you look at it, notice that that wing is not really flying very good. It's not keeping its shape, but it's actually really well pressurized. Collapses are very rarely have anything to do with pressurization. They're almost always an angle of attack phenomenon. And I'm going to show you one here so you understand what you're going through here. Make sure I got the sound off on this, because the air sound gets loud. So this is an early HK prototype, and one of the trade-offs when you design a wing is that you're always balancing performance, stability, and a bunch of other factors. And early on in the HK project, we had some real performers, some stuff that we really liked. It had a much lower passive stability, and as part of that, we decided we had to learn where the boundary conditions were on this. Where did it quit working like we wanted it to? And so one of the things we kept doing is we kept just line set, and we'd change the angle of attack. Another line set, change the angle of attack, until we got to this. And believe it or not, we actually wanted this. Looking back, it wasn't very much fun, but I want you to pay attention as we're watching here. It's a little jumpy, but pay attention to what inputs make things better and what inputs make things worse. And then let's talk. Oh, look at that. We did a little, so the brakes got a little tuck. Oh, wow, rear risers, that looks really good. Nice and clean. Nice and clean. All right. Okay, I'm gonna go brakes here. Oh, whoa, whoa. Get squirrely. Back on rears. We're in good shape. Sorry, the video is a little jumpy. There's a lot of internet traffic going on right now. I'm going to zoom through here to a couple key spots. See here, I went from rears to brakes here, and it's pretty good. And when I allow it to get some pitch changes, that's where things get funky. That spot right there, you would think that I'm adding angle of attack, right? I'm giving brakes slow it down, they pull it back behind me. Not actually always the case. Depends on the airfoil a little bit, but in general, they don't add stability as quickly in the early phases as other methods. So, but oops, here, hold on. So when we get it here to rear riser input, boom, that fixes it right away, right? So that's a little video. I'm going to talk about that a little bit now. So we're going to go into the next page here, and I want to show you a little bit about why this is true. So when you give an input on controls or your brakes, you add angle of attack, but you also change the shape of the airfoil and you add camber. So this does a couple things. It takes the lift vector and moves it back. Remember that lift vector, that big arrow coming out of the middle of the airfoil there is the resolved pressure for all of the wing. And it takes it, moves it backwards. Well, when you've got the wing back here and you lift from the rear, makes it nose over. Puts it to a low angle of attack when it noses over, right? So if I nose over and I got a low angle of attack, what do I enter that zone for negative lift, right? There's a couple of reasons for that. First is just if everything behaves like we exactly want it to, that little curvature out at the tail, you can see down there, back where the trailing edge is deflected, that curvature creates a little bump in pressure. That in and of itself gives pretty nice little pitching moment, a little force back there where you've increased the negative lift, or the negative pressure or lift, which makes it want to pitch forward. But in ram air wings, also in particular, really steep ram air wings, you don't just get a hinge. It's not that simple. You actually, because you're pulling forward, you'll get a little buckle, and that little bump can be exacerbated. If you look at that little photo on the right, that's us tufting one of our prototypes and seeing the airflow on some of that when we were looking at some of these bumps and doing some R&D on that a couple of years ago. And you can see that it accelerates around that back area, and almost all parachutes do this, and speed wings to some degree or another, particularly the steeper ones. This is a more pronounced, but this actually exacerbates this effect here that we're seeing and creates even more of a pitching moment. So brakes actually can increase angle of attack, but at the same time, they can change the pitching moment, and maybe it's not always better. Not all cases is it worse, but by and large, a rule of thumb is that it's not going to be all good. You're gonna lose a little bit of stability and pitching moment when you add controls. Let's look at just adding directly angle of attack. Now, the closest thing that we can do to that on our parachutes is pulling on our rear risers. Speed wings have some more efficient systems for that. They're even more and more directly angle of attack. But if you look at the top picture, that is an airfoil that is basically a zero angle of attack. And you can see that there's some lift on the top, there's some negative lift on the bottom, stagnation right at the leading edge, and the lift is very small. And kind of maybe 25, 27% of the chord right there. When you add rear riser, it moves forward, and all of the downward pressures tend to decrease and the upward pressures increase. So when you add angle of attack directly, you get the increased AOA, but you also get the same effect without shifting the lift vector backwards or adding camber. And so your pitching moment and the thing that makes the wing want to swing forward or back kind of stays the same. If anything, it helps push it and keep that pitching moment upwards. Now, it just so happens that an upwards pitching moment is directly related to our passive stability that we talked about earlier. So the lessons here for that are that in a lot of inputs here, the controls, they can add an angle of attack, but they can, at the same time they're adding angle of attack, they can reduce some of your stability, and it can change the location of your lift vector. Whereas rear risers can add angle of attack and they don't move the center of lift, or if they do, they generally move it forward to a more stable position. So what does this do for us in real life is we're trying to understand how we can control the angle of attack on our wings in less than optimal conditions like turbulence. And the lesson for this is that small brake inputs are not the best method for turbulent flight, or anytime that you need to make sure you have a positive or a high angle of attack, that your rear risers or riser inputs may be a better input because they directly affect that angle of attack without adding any camber or changing the center of lift. Okay? It's kind of our takeaway here from the angle of attack talk. Now, I do want to talk a little bit about angle of attack when wings are flying, because they're going to fly and you don't just do steady state flight, right? And when we're flying around, we're actually varying the angle of attack on certain parts of our wings in flight sometimes. And this is kind of going to be the last thing I'm going to try and shove in your brain, but it's complicated, so bear with me, okay? So when you're flying your wing and you put a bank in, and you're, let's say the low side here is the pilot's turning towards us here in the page, following that flight path. When you put a bank angle in and you start flying like that, on versus steady state flight, when it comes here, that bank angle, the air, this side isn't not going to move as much as this side, because this side is advancing through the air. This side is going to get a higher angle of attack because it doesn't have as much air. Remember, it's just like a air rising. It changes the resultant on that vector. And so you get, on the low side of a turn, you get a higher angle of attack. And on the advancing side, or the high side of a turn, you'll get a lower angle of attack. Why is that important to know? Well, on some wings, paragliders, for example, you have to control that angle of attack on the high side, or you can get a frontal. The passive stability on most parachutes is high enough that you don't get that. But in a really turbulent day, that high side would be much more prone than the low side to the collapses we were talking about earlier. So again, the high side is a low angle of attack. And so what could you do? Well, in paragliding, they add a little bit of high side brake. So for example, if you're learning to do wing overs, which are big turns on a paraglider, you link them together. On this high side right here, they add outside brake as they're coming over the top. And they're coming, that's advancing the fastest, it's getting to the lowest angle of attack. They add that high side brake or riser to keep the wing at a positive angle of attack. On short, low aspect ratio wings, this effect is less pronounced. But as we move to higher and higher angle of attack wings, because the radius between the low AOA side, or low angle attack side, on the low side of the turn, and the high side of the turn gets longer on a high aspect ratio wing, this effect becomes more pronounced, just like swinging a bucket on a rope. As the rope gets longer, same angular momentum, or the same angular velocity, yields a higher velocity on the bucket as the radius gets longer. So when these wings are turning, you're actually inducing differential angles of attack on the wing across the whole wing. I typically will, when I'm flying in a very turbulent day, I will often give brake on the high side as I'm doing a turn. I'll lean in, a little bit of brake or a little bit of riser on the low side to initiate the turn, and then stabilize it with the high side. It's important to note that this need for high passive stability in skydiving hinders performance. Speed wings, pilots will stop flying certain times of the day. Pilots will say, hey, look, the conditions are no good, or there's rotor there, don't fly there. They're much more cautious about when, where, and how they choose to fly. At least the ones that have gotten the proper training are. And just a side note, I'm happy to chat with anybody if you guys ever need references on where to go to get this proper training. We know where it's at. It's out there. It is worth its weight in gold. Okay. But they use that to discern, and they're seeing some advancements in some of their flying stuff that we can't bring into skydiving yet, because the average pilot in skydiving will not active pilot and won't choose when to fly in the proper times of day. So some of my hope of introducing some of this is that we all understand it, we talk about it correctly, and that at some point we'll all be able to exploit some of the beauty of flight that can happen when we play an active part in some of these angles of attack and controlling them for ourselves. So I don't want to go much further than this right now, because we're starting to get into some of the dynamics, and that's a whole other scenario. And I find that if we go too far, we won't get as much sinking in on this and digestion. So I'm going to go ahead and kind of wrap up with that, and say to be continued on some other stuff, and then start fielding some questions.